All right, Farooq, are you there? Farooq, am I audible, Farooq? You can yeah. Uh, okay, I'm audible. And is my file visible? Screen visible to you?
Yes, sir.
All right. Okay. Okay. Thanks. So. Okay, the class ended abruptly yesterday because I had scheduled the class till 9:50 and uh, I couldn't connect back. So there were two questions that were asked towards the end of the class. One was the evaluation policy. I got some feedback that students wanted some quizzes and a reduction in the weightage of the major exam. Uh, and then there was a question about requirements for getting an audit pass. So I'm going to address these two questions. Yeah, so I have kept everybody muted from my side. Yesterday I was watching my video, the class video, and yes, for a substantial period of the class, my voice was not clear. There was some interference, and I also figured out that it was not from my side. So, despite our attempts to identify whose mic was still working, we couldn't find anybody, but there was some voice from student side. So today I have decided to keep your mics muted from my side. If you have a question, you write a message in the chat panel, and I will try to come here frequently and see if there are questions, and I will address them. Yesterday I was not doing it frequently. In fact, yesterday it was my first class on this platform, so I myself was not very familiar. But today I will come frequently and see the chats, your messages, and try to address your queries there and keep you all of you muted from my side. Okay, so this is the course document. I have modified a few things here. So based on the feedback, I am going to keep two quizzes. All right, those two quizzes will be of 7.5 marks each. So if I talk about 100 marks on which finally your grade will be decided, quizzes will be 15 marks, so two quizzes. I'll try to take one before minor and then another one between minor and major exam. Minor I have reduced by 5%. It will be 35 for only one minor, and major 50%. So yesterday I was saying 60 for major. I have followed your feedback, taken that into account, reduced it to 50. All right, so this will be the final distribution of marks or final weightage on which based on which your grade will be decided. Okay, another student was asking about auditing the course. I wanted some time because I wanted to check the minimum requirement prescribed by the dean's office, and it turns out that it is 30% of marks. So I'm keeping that 30%. I'm not changing, I'm not increasing that. But I have put a condition that out of those 30 marks, at least 10 marks should be from the major exam. Okay. I want to keep students involved even if you are deciding to audit the course. See, in normal circumstances, when we have a normal semester, the minimum requirements prescribed by dean's office is that a student must have a D grade, at least a D grade, and 75% attendance. So there was a mechanism to keep students involved in the course, even though if he has enough marks to get a D before major exam, we keep them involved because 75% attendance is required. Now in this semester being online, we cannot use attendance to influence your grades. So attendance is out of picture. But I do want students, even if they have decided to audit the course, be involved with the course material, entire course material at some level. Okay, I don't want some student to get 30% by one minor and one quiz, and then he just doesn't worry about the remaining course material and still gets audit pass. That doesn't make sense to me. So to keep you involved, a student will have to get a peer for major, of course, and at least 10 marks you should get from there, and your total should be 30. Any queries? Any queries? Is it clear? Audit pass criterion? Of course, relative grading will be there as okay. So for uh, A grade, I announced yesterday that to get an A grade, you should be within top 10% of the class, within top 10% of the class, and you must have more than 80%. So both requirements are there to get an A grade. It is in the course document also. For F grade, 30%. 30% below 30%, you get F grade. So there is no relative grading there, but all grades in between will be relative. It will be decided by me where the cutoffs will be placed, and we typically decide based on looking at the distribution of marks. Some other factors play some role there, but the point is yes, the answer to your question is relative grading for all grades in between A and F. Okay, any other question on grading? Audit pass? All right, so no more questions. So I assume we are all in agreement and we are all well informed. This part, so yesterday on Impartus, some of you might have observed, I uploaded this course document, but this place was blank because I wanted to announce it in the class and make sure everybody is all right. So today I will add this part and remove the course document which was uploaded yesterday and upload the new one. So you can refer to this in the coming weeks as well if you need to. Okay, so also tutorial, we decided yesterday we will have every week 2 to 250 Wednesday, but exception is today. Since this is the first week, no tutorial today. Next week onwards, we will meet at this time. All right, so yesterday I gave you some introduction of the course and also tried to give you a broad motivation behind studying, learning about mechanics of fluids. And I said that as we try to derive governing equations and try to do manipulations on those governing equations, we need an idea of the concept of tensors. Okay, so next three classes we will focus on tensors. So what is a tensor? So I am sharing my slide. I hope it is visible. Farooq, please confirm once again, because there's a lot of stuff. My speaking alone will not help students. Okay. All right. Thanks. Thanks for confirming. Okay. Tensor. So a tensor of order n, a tensor of order n in an m-dimensional space is defined to be a mathematical object comprising of m raised to n numbers. M is the space in which you are defining. So if we are defining quantities in physical quantities, we will be dealing with three-dimensional space. So in that case, m will be 3, and then n will be the order of the tensor. And this order could be 0, 1, 2 positive integers. It can be and can be 0 or positive integers. So this mathematical object comprises of m raised to n numbers, which means these numbers depend on your chosen coordinate system. So when we are doing algebraic manipulations on tensors, we often choose a working coordinate system. It could be Cartesian, it could be cylindrical polar, or it could be some other coordinate system of your choice. So you have a coordinate system on using which you are performing algebraic manipulation. So that coordinate system I am calling as working coordinate system or work coordinate system, and it is chosen by the user. Okay, so the value of these m raised to n numbers depend on your chosen coordinate system. Okay, however, note that the tensor as a mathematical entity, we define it to be invariant to the choice of any coordinate system. So the tensor itself does not depend on the coordinate system. For example, velocity of a particle with respect to a frame. You might recall from APL 100 that to define velocity of a particle with respect to a frame, you don't need a coordinate system. Okay, you have defined a vector already. Okay, but then you can express that vector in different coordinate system. You can express VPF in the language of APL 100, velocity of particle P with respect to frame F. You may recall that you can express VPF either in cylindrical coordinate system or a Cartesian coordinate system, and or even you must have studied another coordinate system, path coordinate system. So depending on the coordinate system, the components change, but VPF remains VPF. Velocity of particle with respect to frame is still the same vector. So that's the idea I'm trying to convey. The tensor as a mathematical entity is defined to be invariant to the choice of coordinate system. Now, this invariance of the tensor to any coordinate system that you choose is ensured by a set of rules called the transformation rules of the tensor. So a first order tensor will have its own transformation rule, a second order tensor will have its own transformation rule, but those components, those m raised to n components of the tensor should follow that respective transformation rule. Then only we will call that entity as tensor. Okay. The m raised to n numbers are also called the scalar components of the tensor. Okay, m raised to n numbers are also called the scalar components of the tensor. So in VPF, velocity of particle with respect to a frame, if you choose Cartesian coordinate system, you have V1, V2, V3. There are three components, right? So these three numbers, I'm already using the phrase, they are the scalar components of VPF, the vector in your chosen coordinate system. The m raised to n numbers, which are also called scalar components of the tensor, must follow these transformation rules when we switch from one coordinate system to another. Okay, so this is a constraint ingrained in the definition of tensor. If you change coordinate system, the m raised to n numbers will change. However, they should be related in some manner, dictated by the transformation rule of that tensor. Okay, so this is the definition. It's quite mathematical, but this is how I have to start. I hope it will start making more sense as I take some example. So as I said earlier, for us who will be dealing with quantities relevant in the three-dimensional space in which we exist, so we will be dealing with fluid mechanics in three-dimensional space. Okay, as engineers, we are bothered about three-dimensional space. So in that case, m is 3. But the definition that I had on my previous page, that is a definition, general definition, and many times mathematicians deal with a hyperspace having more than 3 dimensions. In their situations, m could be 4, 5, 6, whatever. But for us, m is equal to 3 because we will be dealing with quantities pertinent only for 3-dimensional space. All right. So in this space, now we talk about example. We take up an example. Velocity of a particle. Velocity of a particle is a tensor of order 1. Okay, n is 1. So in any working coordinate system of our choice, velocity will have how many components according to the definition of tensor? M is 3 and N is 1. M is 3 because three-dimensional space, N is 1 because I'm saying velocity is a first order tensor or tensor of order 1. So it means it will have 3 scalar components, right? And we are very familiar with that idea. Okay, it has 3 scalar components in any coordinate system of our choice, whether it is cylindrical or Cartesian, whatever. The other tensor you are probably familiar with is a stress at a point, and that quantity stress of at a point is a tensor of order 2. Okay, so in my working coordinate system, whatever I choose, stress will have m raised to n, where m is 3, again three-dimensional space, and n is 2, so it will have 9 scalar components. Okay, so a tensor of order 2 in a physical space will have, physical three-dimensional space will have 9 scalar components. Now, a tensor of order 1 is also called a vector. That's the phrase, word you are pretty familiar with. But a vector you can also call a tensor of order 1 in a more general language. Tensors with n greater than or equal to 2, we do not have any special name. So if you have a tensor of third order, we call it tensor of third order. We do use so many words. All right. So only for, well, for vector, we have a special name. And also, you know that if a tensor is of, you might be knowing tensor of order 0 is a scalar. So scalar we can call tensor of order 0. And you will see that if it is a scalar, you know that there is only one component, like density of fluid or temperature. There is only one component. And I'm saying it is tensor of order 0, and it is consistent with this m raised to n framework that I put earlier. M is 3, n is 0, 3 raised to 0, one scalar component. In fact, for tensor of order 0, m is irrelevant. M could be any number, but since it is of order 0, it will only be having one component in any m-dimensional space. All right, so some examples of tensors of order 0, 1, and 2. Let me go back here. How we will decide the order of a tensor. You don't decide order of a tensor. You come across quantities where you realize that to describe it fully, you will need 3 components or you will need 9 components. For example, stress is what? Stress is force per unit area, right? So force itself has 3 directions, and then the area also you can choose in 3 ways. You can choose an area which is perpendicular to x-axis. On that area, you can have force in 3 directions, right? So when you are dealing with something like stress, you end up having 9 components. So it's not that you decide, you encounter while deriving equations or while learning physics, you encounter quantities which has so many components. Okay, I hope I have answered your question. All right. Okay. Any other questions so far? And again, where I am reading the note PDF file, they are going to be uploaded. So even I'm not following everything, I don't really expect you to follow 100% of what I'm saying, but like 30-40% if you can grasp, and then if you go and read my notes, I think you will be able to understand everything. Okay, but do feel free to write your questions. I will keep coming back once in a while. All right. So this I've already said, tensor of order 0 is called a scalar. Now in fluid mechanics, like other branches of science, you may come across tensors of order greater than or equal to 3. Towards the very end of the course, we will come across some tensors of order 3. If you take a course in advanced fluid mechanics, something like turbulent flows, even CFD, computational fluid dynamics, over a substantial period of the course, you will be dealing with tensors of higher order. Okay. Now, how do I express a tensor in coordinate system of our choice? The question, maybe some of you may be having a question, why do I express tensor? Why do I need to express tensor in the coordinate system of our choice? The answer to that is I said something like that earlier also. To do algebraic manipulations on tensors, we find it convenient to choose to use a coordinate system of our choice, right? Like sometimes you use, for some problems in mechanics, you chose a cylindrical coordinate system, in some you choose Cartesian, but you do choose a coordinate system to do algebraic manipulation. So same will be the story here. So we will have to perform the algebraic manipulations on tensors, and for that we will need a coordinate system. So how to express tensor of any order in a coordinate system? That's the topic I'm going to take up. So for simplicity, let's take a Cartesian coordinate system, and my hope is that the ideas that I discussed with reference to a Cartesian coordinate system, you will be able to extend it to other coordinate system also. This being the simplest one, that's what we take initially. So I have a Cartesian coordinate system with which I am denoting like this. And again, this is legacy engineering mechanics. O is what I write here. O is the origin of the coordinate system, and E1, E2, E3 are three mutually perpendicular unit vectors. E1, E2, E3 are three mutually perpendicular unit vectors, and x1, x2, x3 are coordinates of an arbitrary point P in space. X1, x2, x3 are just numbers, three scalars. So this is how we will denote this is the notation for our coordinate system. Okay. Now, if T is a tensor, let's start with T a tensor of order 1, which is a vector. Again, for simplicity, so that I can illustrate the ideas on this and then extrapolate that for higher order tensors. If T is a tensor of order 1 or a vector, how do we express this tensor in the coordinate system? You already know that. This is how you will express. T is the tensor of order 1 or vector. You will write it as T1 E1 plus T2 E2 plus T3 E3. Right? And we know that T1, T2, T3 are three scalar components of the tensor in this coordinate system. Now, in this course, I want to make it clear that I will be using an underbar to represent all tensors of order n greater than 1. So I will not make any distinction between, as far as symbol is concerned, for a vector or tensor of order greater than or equal to 2. For all tensors, I will just write an underbar. In some textbooks and in some people, for vectors, they still put an arrow at the top, and for tensors of order greater than or equal to 2, they put an underbar. They make this distinction, but for to me it doesn't make much sense. I just use the common thing. So for all tensors, except of course tensors of order 0 scalars, I will use an underbar. So for velocity vector will be written as v underbar, and a stress tensor will also be written as s underbar. So you may be wondering, then how do I, if just looking by V and S, just looking by V underbar and S underbar, how do I know the order of the tensor? The answer to that question is you cannot know. You cannot guess just by looking this. If I don't tell you it is velocity vector, if I just give you V underbar, all I am conveying that V is a tensor of order n greater than or equal to 1. Whether n is equal to 1 or 2 or 3, that information will be available from context, not from the symbol itself. And you will see most of the time we will be having an idea what order tensor we are dealing with, or somebody tells you upfront that this is of that order. Okay. All right. So in this representation, what we have used is, of course, we have on the right hand side what entities or what quantities appear. You have T1, T2, T3, which are the scalar components, that m raised to n components, and you have E1, E2, E3. So E1, E2, and E3 form a three-membered basis to represent tensor of order 1. So you take each one of these basis members. So E1 is one basis member, E2 is another basis member, E3 is another basis member. You take each of these basis members, multiply it correspondingly by its scalar component, and add all of them up. This is how you express a tensor of order 1, right? And again, the T1 is also called, in this case, component of T along basis unit vector E1. T2 will be called component of T along E2, and T3 will be called component along E3. You are familiar with this. I'm reviewing it because, as I said, I will be extrapolating this idea when we go to higher order tensor. So the coefficient of E1 is called component of tensor T along basis member E1 component, and so on for other components. T1, T2, T3 themselves are just numbers. Now, there are two questions I want to ask. Do T1, T2, T3 depend on our choice of coordinate system? Yes, they do. If I change the coordinate system to something else, you will have three numbers, but those three numbers should be written as T1 prime, T2 prime, and T3 prime rather than T1, T2, and T3, because in general they are different. Does the tensor T depend on the choice of coordinate system used to express it? No. This is part of the definition. If T is a tensor, the tensor itself, this going back, this sum of three terms like this, that is invariant to coordinate system. The tensor remains the same. The velocity of particle with respect to frame remains the same. What changes with the coordinate system are individually T1, T2, T3, and of course the basis unit vectors will also change with coordinate system. But when they are added, when the components are multiplied with the basis members and added in this manner, it should remain invariant. It should be independent of coordinate system. All right, so that's the idea I'm putting more formally here. So now I have two coordinate systems. The first red one is my original Cartesian coordinate system, and now I have come up with another Cartesian coordinate system which I have shown in green color here. Okay, and following the same notation, I will denote the new coordinate system in this manner. I hope it makes sense. O is origin, so I have not changed the origin. Origin is the same. I've changed the unit vectors because it's a new coordinate system. Those unit vectors are primed, E1 prime, E2 prime, E3 prime, and this has some arbitrary orientation with respect to the red coordinate system. And once you have changed the unit vectors to prime, in general, your coordinates x1 prime, x2 prime, and x3 prime are also in general different from x1, x2, x3 that we had earlier. Okay. That's what I have written here. Both coordinate system have the same origin, though this set x1 prime, x2 prime, x3 prime are coordinates of point P, for which coordinates in the original coordinate system were x1, x2, x3. And in general, x1 prime is not same as x1, x2 prime is not same as x2, x3 prime is not same as x3. Okay, Farooq, is my cursor visible? Because I am using it. When I'm speaking, I am moving the cursor, hoping that students are able to see on the PDF file. Okay. I just hope by keeping the cursor on the words which I am speaking or explaining, it is easier on your part, students' part, to understand. All right. So this is, in general, these three are different. Okay. All right. So now if I want to express the tensor, as I was saying earlier, in the new coordinate system, the tensor remains the same. I want it to be the same. That's how it is defined. If it is a tensor, it has to remain the same. So I'm using the same symbol T underbar on the left hand side. But now in the new coordinate system, I am writing RHS in this manner. Okay. And recall that in the original coordinate system, I wrote it like this. Right hand side was T1, T2, T3, no prime. And in general, these primed and unprimed components will be different, right? But then the question is, they are different, fine, but is there a relationship that exists between T1, T2, T3 on one hand and T1 prime, T2 prime, T3 prime on the other hand? Is there any relationship? And the answer to that question is yes, they must be related. How are they related? Through a transformation rule. Through a transformation rule. So if you go back to my definition of a tensor, on the very first slide or first page that I showed, I said that the m raised to power n components should follow some transformation rules. So that is the transformation rule I am talking about now. That is the transformation rule is the rule or the relationship that relates T1, T2, T3 on one hand to T1 prime, T2 prime, T3 prime on the other hand. Okay. So I will derive this. I will show you what the transformation rule is for a tensor of order 1. Okay. But before we find the transformation rule, let us write, just to reduce algebra, I want to express T in a more compact manner. Okay. And that compact manner I am going to use, for that compact manner of writing, I am going to use this symbol sigma. I hope you are familiar. The sigma, so I am writing T as the sigma TIEI. So I have brought in indices. Instead of writing hard numbers 1, 2, and 3, I am using indices like variables in a computer program. TIEI, where I will take values over its full range. The range of I is what? T1, T2, and T3. Okay. So in that manner, I can write T as TIEI summation, and then you will observe that once you write it in this manner, summation, and I is an index which takes values from 1 and 1 to 3, you can actually write it as TJ, also. I mean, there is nothing great about I. You can also use J or some other index. All you have to do is to give this information to your reader that this is the variable which will take its full range from 1 to 3. So these two are equivalent notations. Okay, so now with this notation, we have to write less, but the meanings are the same, or what we want to convey remains the same. We go back to the red and the green coordinate system, and the same tensor can be expressed as T as TIEI, and in the other coordinate system it should be Ti prime EI prime, summation over 1 to 3. All right. Okay. So remember, we are chasing, or we are trying to find the transformation rule. So let us define 9 numbers, A1, A11, 12, and so on. So I have defined 9 numbers with 2 indices, and those indices can take value from 1, 2, or 3. And how do we define these 9 numbers? I define it in this way. So these are actually direction cosines. Again, legacy APL 100, you must have done something like this. E1 prime, so basically to express the first unit vector of the green coordinate system in terms of the unit vectors of the red coordinate system, I need these coefficients, these direction cosines. All right. And then you have to pay a lot of attention to what is happening to the indices here. So this is E1 prime. I want to write in terms of what? E1, E2, and E3, unprimed. And for that, I am having these numbers here, or these coefficients here, A11, A12, A13. So you see this second index of A matches with the unit vector. And the first index of A in all these 3 terms is the same as the prime unit vector for which I am writing this expression. All right. Similarly for E2 prime and E3 prime. So Aij is actually the cosine of the angle between Ei prime and Ej. I can write it like this. So I will let you stare at it for a few seconds and make sure that the indices are right. I hope I have written them correctly. All right. So as I said, Aij is actually the direction cosine of the angle between Ei prime and Ej prime. And we can show that very easily by, if you take the dot product of 1, with E2, dot this first equation with E2, unprimed on both the sides, what I will get, E1 prime dot E2, which will be kept there. On the right hand side, E2, when dots with E1 is 0, because they are mutually perpendicular, dots with E3 0. So the only term which is left is A12. So this is how we have defined A12. In a similar way, we can show that E1 prime dot E1 is A11 and E2 prime dot E2 is A22. Okay, so the first index of A comes from the index of the primed unit vector and the second index comes from the unprimed unit vector. Okay, so thus in general Aij is Ei dot Ej, where Ij can take any value from 1 to 3. Okay. So effectively, these 9 numbers have information how the two coordinate system, the primed and the unprimed, are oriented relative to each other at the given instant. So it has the information about all the direction cosines between the 3 unit vectors of first and the 3 unit vectors of the second. Okay, so let us start with the expression of t. So again, trying to get a transformation rule. I need something in between, so I get that, and then I try to remind you that I'm trying to find a transformation rule. So now I start with the expression of t in the green coordinate system. And now I'm going to substitute all primed unit vectors in terms of unprimed unit vectors using Aij information. Okay, so Ei prime, which I wrote earlier, was this. And then you note this also I can write in a compact manner as A1I Ei, right? This E1 prime can be written in this compact manner as A1I Ei. So that is the overall goal here, to write primed unit vector in terms of all 3 unprimed unit vectors. Similarly, E2 prime can be written in this manner and E3 prime can be written in this manner. I will leave it for a few seconds. Let me go back and check if I have questions. Okay. Any questions, please type your message there. Okay, so these things are going to be substituted by these things in this star equation. And when I do that, this is how it starts looking like. All right, these things being replaced by these here, and it starts looking like this. So it still has T1 prime, T2 prime, and T3 prime as coefficients, but instead of E1 prime, E2 prime, and E3 prime, we have some combinations of unprimed unit vectors and Aij components or Aij numbers. So next what I'm going to do is I'm going to collect the coefficients of E1 separately. So on the right hand side, there are E1, E2, and E3 appearing more than one time. All right, so I'm going to, my motive is to collect everything that has coefficient as E1, or rather everything that is coefficient of E1, I collect separately. And you will see that if you pay attention or you give it some thought, you will see that the coefficient of E1 will be what? One E1 will come from here, one coefficient of E1 will come from here, another from here, and another from here. The one that comes from here will have what? I will be 1. So A11 to T1 prime A11 contribution is from this is coming from here, this is coming from here, this is coming from here. Okay. And then you observe the indices and see that I can write them in compact form, which is Ti prime AI1. And I want to use this opportunity to tell the students that these are all my handwritten notes, which I write typically a day before my lecture. So there is always a possibility that there may be mistakes in writing, mistakes which are unintentional. It's just that while writing, I was in a little hurry, and instead of I1, I write 1I. Such things are possibilities. So when you read my notes, be critical about it. be critical about it. So if you are not finding something reasonable, don't just accept it. It may be that I have made a mistake. So correct them, and it will be good if you let me know. I will also tell the entire class, or I will go back to the notes and make a correction. So in that way you will be helping me. So do pay critical attention to all these indices. There will be a lot of such material in this course. Okay, so coefficient of E1 I have collected like this. Similarly, I can go to this double star equation and collect coefficients of E2, and you will find out that they turn out to be this. Okay, Ei prime AI2 summation, and then coefficient of E3 in this. Similarly, you can extract, and they will turn out to be this. All right. So once you have that, once you have the coefficients of E1, E2, E3 unprimed, now I can just re-express equation double star in this manner. Okay, so this is coming from here, this is here, and this is here. Okay, so what is the difference between this expression on the top? What is the difference between this expression on the top and this expression? Expression wise, I mean the quantity, the tensor is of course summation the same, left hand side is same. Right hand side, what difference I have made? I have gotten rid of EI primes. That's the difference I have made. I have replaced all EI primes in terms of EI. I went back to original coordinate system in terms of unit vectors. And then recall that in the red coordinate system, when I was using E1, E2, E3, initially I had T1, T2, T3. I didn't have any prime there because prime is all primes are children of the new coordinate system. So originally when I wrote this expression, I had T1, T2, T3. Thus, for T to be independent of the choice of our working coordinate system, right? We had two working coordinate system, but this is part of the definition of the tensor. If that it should remain invariant. So if it has to remain invariant, it means that this plus equation here and the two pluses here have to be identical, right? Further, in plus and 2 plus equations, I have E1, E2, E3 same. I mean the unit vectors are the same, which implies that this equation equating plus and 2 pluses actually gives me 3 scalar equations. And these 3 scalar equations are actually putting a constraint or tying together or giving us a relationship between unprimed components T1, T2, T3 and primed components T1 prime, T2 prime, T3 prime. So T1 is this, T1 prime, you have Ti primes here, similarly T2 is this, and similarly T3 is this. And then you will see that instead of writing these three separately, we can use an index form again with summation symbol. You can in general represent these three equations by one single index equation, Tj equals Ti prime Aij, summation I equals 1 to summation with I going from 1 to 3. All right. So this is the transformation rule for a tensor of order 1. Any tensor of order 1. Velocity, force, whatever it is, if you are changing your coordinate system, if you define that quantity to be a tensor of order 1, then the components should change according to this rule. All right, that's the statement I'm making here. And again, my lecture may sound repetitive because I say a few things and then I have these things written and I say that again. But mind you, I do it, I write things. So my primary objective is to write everything that I can possibly speak, so that when you have access to my notes, you can kind of relive whatever I said, and you have reference material for all the time. So my notes are typically more wordy to help you. And since they are more wordy, when I try to speak using them, I speak sometimes before those words come, and it may sound repetitive. So please bear with me. Eventually, it is being there. The repetition is there in a way to help you. All right, so thus the m raised to n, which is three components of components T1, T2, T3, and the three components T1 prime, T2 prime, T3 prime represent components of the same tensor in two different coordinate system if this set and this set are related like this. This is the transformation rule. All right. Now with this idea, let's go to a second order tensor. How do we express a second order tensor in a Cartesian coordinate system? So at least one example you have, that of a stress. Okay, but probably despite being aware of that example, my guess is might not have come across how to express that tensor in a particular coordinate system. All right, so that is what we will do here. So first of all, if it is given that T is a second order tensor, somebody tells you, again going back to the question that student asked, don't worry about how to figure out. Somebody has told you it is a second order tensor. So second order tensor will have 3 raised to the power 2 components, right? 3 is the three-dimensional space and is second order tensor, so it will have 9 scalar components. Now if you think about it, E1, E2 and E3, so to express this tensor in this coordinate system, I need scalar components as well as I need basis members. You may recall in vectors, I needed T1, T2, T3, and I also needed basis members. Basis members there were at that time were unit vectors themselves, E1, E2, E3. But if you think about it now you have 9 scalar components. But even E2, E3 on their own, they are only they can make only 3-member bases on their own. All right. So that basis of E1, E2, E3 is not good enough for a second order tensor. I hope you realize this. Now, for expressing a second order tensor with 9 components, we need a new basis. Okay. New basis with 9 members. And thus, this 9-membered basis is formed with what is called 9 dyads. So I am bringing a new concept here, 9 dyads. What is a dyad? A dyad is an ordered combination of 2 unit vectors. What is an ordered combination? Example is E1, E2. So I am taking 2 unit vectors and making a new entity out of it, a new basis member, such that here E1, E2 are just standing next to each other. Mind you, this is probably a new concept for all of you. E1 and E2 are not doing anything to each other. They're not dotting with each other. They're not crossing with each other. They're not doing anything. They're just standing next to each other. In this way, so in this way, we can create 9 different dyads using combinations of E1, E2, E3. So if I start making a new quantity, a new dyad in this fashion, it will turn out that with 3 unit vectors, you can construct 9 such members, which I have written in this manner. 1, 1, 1, 2, 1, 3, 2, 1, 2, 3, 2, 2, 2, 3, and so on. All right. And mind you, they are not doing anything to each other, just standing. So it's like there are 2 people and I have just just put a rope around them and I'm saying this is a new entity, 2 members. One facing east and another facing west, something like that in a manner of speaking. Okay, and using these new basis members, the tensor T of second order is expressed like this. So what do we see here? So it has some similarity with the expression of a first order tensor. The similarity is have a scalar coefficient multiplied by a basis member that I had in a first order tensor, T1 E1, T2 E2, T3 E3. Here I have T11, T12, T13. There are 2 indices running, each index going from 1 to 3, so that I have 9 components. And then these indices, like there it was T2 E2 for first order tensor. Here we have T12. T12 means it is the coefficient of that basis member, which is a dyad, and it is E1 E2. Now contrast this with T21. T21 is the scalar coefficient of that basis member which has been constructed with E2 coming first and E1 coming second. Okay, and that's what I have written. Mind you, this dyad is formed with an ordered pair. So E1 E2 is not the same as E2 E1. Order matters. All right. And again, repetition, T12 is the scalar component of tensor T along the dyad E1 E2. T21 is the scalar component of tensor T along the dyad E2 E1. All right. Okay, so time is up. I will leave this slide here for a few seconds and then I'll see if I have questions. Yesterday, I had scheduled the class till 9:50 and it abruptly ended. Today, I've scheduled it till 10, and I know that you have classes starting at 10. That's what I remember from 2017. Students used to go to another class, but we have 10 minutes. Students who have to leave early, when it is 9:50, you are free to leave my class. But students who have questions, you may ask questions. I will be here till 10 a.m. So this session will last till 10 a.m. Okay. So if we use this time for interaction, if you wish to. Okay. All right. Now let me go back here, see if there are questions. Physical significance. Right now, there is no physical significance. Even E2 has no physical significance right now because I am dealing with it at a very mathematical level. Even E2 will start having significance when you are dealing with physical quantities. For example, if it is a stress tensor, suppose stress tensor I denote by S, then what it will have according to the expression, what I just wrote, it will be S11 E11, S12 E1 E2, and so on. There, once you have a physical quantity, you can associate some meaning, and that meaning will be, so we know that stress is force per unit area. So S12 means what? S12 means on a surface which is perpendicular to two axes or second axis, on a surface which is perpendicular to two axes, the force component in one direction, right? That's what it means, S12 component of stress. With that, you can associate some meaning that E1 and E2, so E2, the first unit vector E1 is denoting the direction along which the component of force being reported in S12, and E2 is the unit vector perpendicular to which the surface is being considered for reporting that stress value. Okay. So given specific quantities, you can associate meaning. Right now, there is no physical meaning. I hope I have answered your question, Akash. At this point, I can actually disable, I can unmute you all, because now even little disturbance we can handle. So if you feel, well, second one or first, Akash, the second one is normal. Now that depends on, I mean, context. Sometimes people take the second one as normal. Sometimes they take the first one as normal. We should take something and we should stick to that. That is not important here. What is important here? You please grasp the idea. There is no physical meaning right now. In terms of quantities like stress, one unit vector will denote the direction along which the force component is being considered, and the other one will denote the direction perpendicular to which the surface is. Okay, Akash, Amitesh, isn't it easier to use matrices? Indeed, we will use matrices, but mind you, matrices are, when you use matrices to denote tensor, implicitly you are using this expression, Amitesh. That's what happens many times. When tensors are introduced as matrices, you do not get this idea that behind the scene what you have is this expression. I will also do that. I will also start using matrices, but matrices will be shorthand. So at one point I will say that instead of writing T as T11, E11, E12, all this, I will say that let's have an agreement that it is known, it is implied. We know that in the background, the basis unit vectors are E1, E1, basis dyads are E1, 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 E2, and so on. Let's not keep repeating that. Instead of writing this right hand side like this, let me just put the scalars as a matrix form. So it is a shorthand. It is more convenient. So your question, technically the answer to your question would be yes, it is convenient. But I spend so much time, or we are spending so much time on it to tell you that what lies behind. I mean, what is the full expression? So there are dyads behind. That's why I wrote this expression. I hope I have answered your question, Amitesh. Yes. Akash, okay. Sarthak, even E2 must only be orthogonal, or it can be any vector. What do you mean by that? Even E2 must be only orthogonal, or it can be any vector. Acha, are you asking, Are you asking, Sarthak, that E1 and E2 mutually, the two unit vectors that we are using to construct the dyad, should they necessarily be unit vectors? Yes, should they necessarily be orthogonal vectors? Is that what you're asking? Yes, they must be. Yes, they must be. Then only they will form a member of the basis. It is something like for vectors. You will, when you write T as T1, E1, T2, E2, T3, E3, E1 and E1 and E2 should be mutually perpendicular. Then only you will say that they form a basis. They don't have any component along each other. So the same thing is here. This E1, E2 that we are using to construct the dyad, they should be mutually perpendicular. Have I answered your question, Sarthak? Yes.
Uh, Sir, for the set of vectors to be basis, they should be linearly independent. But we here you are talking about orthogonality. So, sir, um, orthogonal is more constant than linear independency. So that's why I am asking.
Uh, No, if you are using non-orthogonal, let's talk about only vectors for the time being. If you are using non-orthogonal vectors, then the components that are coming, like T1 and T2 and T3, they remain independent of each other or not? If you are not using orthogonal, I think they will have some components along each other. I mean, but T1 will have T1, T2, and T3 will not remain independent. So you can write, you can make a basis with non-linear unit, non-planar, right? What do you say that? What is the condition you talked about?
I talked about that for set to be basis, we can choose only linear independent vectors. So why we are choosing orthogonal? Linear independent vectors can also form a basis.
Well, let me think how to answer this question. So let me ask you this: why do you, under what conditions or for what advantage do you form? Would you like to form a coordinate system with non-orthogonal unit vectors? What is the advantage? Probably that will help me answer your question. Right now, I don't know how to answer. So you tell me first. Why would you like to construct a coordinate system in which the unit vectors are not
Because
necessarily perpendicular, but they are just independent, linearly not dependent on each other? What is the advantage? What is
sir,
the advantage?
in sir, in many cases we have advantage because
Hmm.
orthogonality is more is more constant than linear independency. We can easily find linearly independent vectors, but it is harder to find orthogonal vectors because we have to apply Gram-Schmidt orthogonalization. But we can easily find linearly independent vectors.
Well, in that case, if you can easily find such linearly independent vectors are not mutually perpendicular, and you use that to construct your basis for coordinate system, in that case, you can extend this idea to even second order tensors. In that case, E1 and E2 need not be perpendicular if you have some advantage. That's what my answer would be, that if you insist on doing that, you can do it. But right now, what I am talking about and the algebraic manipulations that I will be showing, very soon I will be doing dot product and cross product, a double dot product and so on. There, all the time I will assume that these unit vectors are mutually perpendicular to each other. So for my context, I would say they are mutually perpendicular. But as I said, if you have some advantage of constructing a basis with just linearly independent unit vectors, then you can extend this idea and you can try to express your tensor in this manner also. And there you can construct your dyads using those non-orthogonal but linearly independent unit vectors, hoping that you will reap the same advantage that you had for vectors. Have I answered your question in some way? Yeah, see, as you said, let me add a few words. As you said that when you are not able to find mutually perpendicular vectors, then you live with compromise and you get a linearly independent unit vectors and construct a coordinate system. So my response to your question is that right now that is not the problem with us. We know three mutually perpendicular unit vectors, and that is a coordinate system constructed with mutually perpendicular unit vectors offer lesser algebraic issues, and that's why I am using mutually perpendicular unit vectors. Right? Okay, lecture is over.